In the last class, we started looking at our subshells and filling in our diagrams. So if we draw it like this, this will really help us when we come to some of the subshells that start penetrating into the lower shells. And that's something that we have to consider when we're drawing our electron configurations. So I showed you this. So today we will start looking at the periodic table and using the periodic table to do this, which I'd rather. But that's just what we're representing. And it really becomes important when we get here. Because for 1s, 2s, 2p, 3s, 3p, we don't have any penetration. But then 4s will get into and be lower than our 3b. So then we go up to 3b. So that's when it becomes really important. If we're looking at a molecule or an atom in the first two periods, then this concept of the penetration isn't really going to come about. And it's really as we get into higher energy levels that the difference between the energy levels starts getting smaller. So let's look at some examples in the little corner. I have that drawn out. But all of these, lithium, beryllium, boron, and carbon, they're all in the second period, the second row of the periodic table. So we don't really have to worry about penetration so much. So lithium has 3 electrons. You might need a review from the beginning of the semester to figure out how it has 3 electrons, but you should know that from looking at the periodic table. So our 1s and 2s we can fill in with 2s is fully full. 1s is full, 2s isn't. So our electron configuration is our 1s2, 2s, and we only have 1 electron in that higher energy level. If we look at beryllium, we have our 1s2 and 2s2. Now that's total of our 4 electrons, so we don't have any filled p orbitals, though p is an option, it's just not filled because we're higher in energy. So that's what we see. Now if we look at boron, we actually have 5 electrons. So our 1s2 and our 2s2s are both going to be full, and we still have an electron left over, so we do have our 2p, and we have 1 electron there, for a total of 5 electrons. And this is what our orbital diagram would look like. And we're increasing in energy, so 2s is higher in energy, and 2p is even higher. And then if we look at carbon, we have 6 electrons, so we have 1s2, 2s2, and then we're left with 2p2. And again, this is what our orbital diagram would look like. Let's look at manganese and do the electron configuration, the full ground state orbital diagram. So if we look for manganese on the periodic table, we see it's in that 3rd period. It's in group 2. It's right under beryllium. So our first step is, how many electrons do we have? Because we need to know how many electrons we have so we can fill this out. So our Z for manganese, I said magnesium. Manganese is number 25. So that's in the transition metal area. So our Z is 25, so we have 25 protons, and if we have a neutral atom, therefore we have 25 electrons. So our S subshell holds 2 electrons, just to review. Our P subshell, we have those 3 boxes, so a total of 6. Our D subshell has a total of 10 electrons, and that may or may not be important to this one. We'll have to see. And our F subshell has a total of 14 electrons. So that's just a reminder. That's the total that any of those subshells can have, based on the fact that each orbital can only have 2 electrons. So for F, we have 7 orbitals. So we can have 14 electrons in there. So starting with 1s, that's going to be full. Then we have our 2s that has 2 electrons. And then our 2p that has a total of 6 electrons. And then, following this diagram, then we're going to have 3s. So total, that's 12 electrons. And I'm just keeping track of the amount of electrons that I've already used because I'm trying to get to 25. So clearly our total amount of electrons won't be more than 25. And then we'll go 3p, which again can have 6, and then 4s can have 2. So right now I'm at a total of 20 electrons, but I need 5 more. So I am getting into that 3d, but that 3d won't be full because I only have 5 electrons to put in it. If I fully fill it, I'd have 30 electrons, and that's not correct. So I'm only going to have 5 electrons there. So based on the order of subshell filling, what we need is the first 7 subshells. So what we have is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and again at this point I'm only at 20 electrons, so now I have to go up to the 3d, but I have 5 electrons I need to put in it. Remember, as we fill before we go to the higher energy level, so that's how I just drew all of these filled. Because we wouldn't get to the 3D energy level until we filled everything under it, because we fill as we go up. So this is the full electron configuration, meaning I'm drawing all of them. We can also draw it with our argon, and then only including everything after argon. So that's also the option, but this particular one asks for the full ground state diagram. We can fill these in. These are all of these. And again, we are filling our lower energy levels and pairing them before we go to the next one. So that's why we fill 1s. We're still on magnesium, by the way. I mean manganese. I don't know why I keep on doing that. So now we're just mapping this out, what I just drew. Then we're going to go up to the next highest energy level, which is our 2s. Once we get to 2p, we know it's going to be completely filled, but I like to continue with filling unpaired before I pair for degenerate, just so I'm used to it and I don't make the mistake when it matters. So I'm going to show it all half filled, but eventually it's going to be completely filled. Then I can move up to 3s. Then I can go to 3p, and then I can move up to 4s. So now I'm at 20 electrons, and then the correct configuration is all 5 of my electrons unpaired for 3d, because we do not pair until we completely fill all of the degenerate orbitals. So this is the correct electron configuration for manganese. So this is just written what I wrote earlier. And that's the full electron configuration. The shorthand would be to write argon in our brackets, and then whatever argon doesn't have, which is 4s2 and 3d5. So that is the shorthand to write it, because argon's electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p6. So we can put that in parentheses. So that's pretty common that you might see the shorthand. But this particular question did ask for the full ground state. So that's the total there. So when we looked at bromine, this was the answer. You answered this one in the last class. So again, bromine is part of our halogens. It has an atomic number of 35. So it has a total of 35 electrons when it is neutral. And this is just a reminder as you're going through these. Now, I know I only showed to here 4 because bromine is in period 4. So I know I'm not going to be going further than 4. So I'm not even writing it down. So again, following this, we have our 1s2, gives us 2 electrons. Then our 2s2, that's another 2 electrons, so that's a total of 4. Then our 2p6 and our 3s2. So that gives us a total of 12. And this is my total. And then my 3p6, 4s2, that's another 8. So that's 20. So I have to keep on going because I'm only at 20 now. So 3d10, that's going to give me 30 after 3d10. If I fully fill that 4p to 6, then that would give me 36. 36 is too much. We only have 35. Now we're going to talk about charged species, but at this point we're wrapping out the neutral species. So that 4p only has the 5. And again, if you add up all of these superscripted numbers, it will come out to your total amount of electrons. That's really important. If you look at D comes out to 36. So that's too many electrons. We're mapping out the actual amount of electrons in our group. That's our total electron configuration. Our valence electrons are the electrons in our highest principal energy shell. These are our most outer, typically, electrons. And these are going to be our electrons that have the most shielding from the nuclear charge in the middle. And typically, when we're going to look at reactions, these are going to be the available electrons. Or the outermost energy shell can accept electrons, or it can come from those electrons. So as chemists, even though the full electron configuration is useful to figure out what's completely going on in the molecule, when we're predicting bonding, either ionic or covalent, what we're typically looking at is the valence electrons. The core electrons aren't as accessible when we're looking at typical chemistry. It's not talking about other types of chemistry like nuclear chemistry, but when we're talking about typical chemistry, we're usually looking at what's going on in the valence, what's going on in the outer shell. So what we're looking at, not just the shell that's further out, but our principal energy shell. So if our highest principal energy is 4, our valence electrons are going to be in 4. So that's what we're looking at. Electrons in the lower shell, we just call them core electrons. They're more in the center. And one of the most important factors of reactions is going to be what's going on in this valence. So we're going to look at that in more detail. So if we look at krypton, bless you, this is our full electron configuration. Krypton is one of our noble gases. It's number 36. So we have 36 electrons in the neutral species. Well, we really don't form a lot of charged species with noble gases. They're pretty much not reactive. And we're going to look at why that is. But our valence electrons are the electrons in the highest energy level, which is 4. So even though 3D is written after 4s, it's not considered part of our valence electrons. We're looking at the electrons in the highest energy level, which is 4. So that's our 2 electrons in 4s and our 6 electrons in 4p. And for krypton, we have a total of 8 valence electrons. And that 8 is going to be really key for our later discussions. So we have 28 core electrons, 8 valence electrons, and a total of 36 electrons in krypton. The group number corresponds with the number of valence electrons in each atom, which was why for our principal group numbers, we can use the group number to determine whether our atoms would lose a certain amount of electrons or gain a certain amount of electrons. So we're going to look at that in more detail. But that's one of the reasons why we're able to put and see recurring reactivity as we go down a group in the periodic table. It has to do with the fact that all of those atoms in that group have the same number of valence, and therefore they have the same type of reactivity, which is why we're able to put the periodic table in this order and be able to predict reactivity. Now there are things that are slightly different about them. And we're going to look at that, including size. The amount of electrons that are core can also affect our reactivity. But we see general trends as we go down the periodic table because all of those atoms have the same number of valence. So the number of columns in each block is the maximum number of electrons that a sublevel can hold. So if we look at this, this represents our S block. Helium actually is a noble gas, but when we're looking at it based on the S block, we could think about it as being here. So we can have a 1s1, 1s2, and that S can only hold 2 electrons. Here we have 2s1, 2s2, and that represents how many electrons the S block can hold. And so on, 3s1, 3s2, 4s1, 4s2. And so on with that. And that tells us the sublevel. If we look at these are our P, 1, 2, 3, 4, 5, 6. And as we go over, we see 2P1, 2P2, 2P3, 2P4, 2P5, and 2P6. And that's in agreement with what we were doing before. So that block can only hold 6 electrons. And it is represented with that quantum theory. The period number corresponds to the principal energy level. This is principal energy level 1, 2, 3, 4, 5. Now remember, potassium has electrons in the lower principal energy levels, but its outermost principal energy level is 4. Same thing if we go across. This is still 2, 3, 4, 5, 6. And we don't really have anything here, but eventually we might, and we could predict. Well, they're sort of there, unknown, shown in this periodic table. But we can predict their properties because TS unknown, 117, is under AT. So we have some ideas of what it might look like. So you can use your periodic table to figure out your ground state electron configuration. So here's another example. Here's V. Again, having a periodic table for these discussions will help you. You can also use the ones there, but I'll help you out. V is number 23. You can't find it. So again, this is just our blank periodic table. Helium is S2 for that principal energy level of 1. It acts like the noble gases, and we're still going to discuss why in this chapter, why it goes over there. And hydrogen's a little odd too. So those two principal energy level of 1, those two atoms are a little odd with their placement in the periodic table. For example, hydrogen is what we consider a non-metal, even though it's over the metals. So there are some issues with those two first ones. But the reason why is because they only have one orbital. They only have that one s, and that one s can either have 1 electron or 2 electrons in it. They don't have anything else. All the other ones are 2 and above, so they have at least 2s and the ability to have 2p, even if they don't have electrons in it. But the principal quantum shell of 1 is special. Now the D's we're going to talk about. And again, notice that there are 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 D in this block. And that again represents the fact that we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 electrons filled in that D orbital. Now the principal quantum number, we'll talk about that in a second. I'm going to skip that for now. And then F's, we have a total of 7. 14, 1, 2, 3, because we can fit 14 electrons in it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And we're going to talk about that weird F14D1 also. So if we look at something like neon, and we're using the periodic table, we can use the way I showed you earlier, or we can use the periodic table to represent our electron configuration. So neon, we're going to have our, if we're trying to figure out phosphorus, neon's our first noble gas before it, so we can put neon in our parentheses, in brackets. Now you can do the full electron configuration going all the way from 1s1, but typically, especially as we get to lower atoms here, then you're going to be doing a really long electron configuration, and it's not necessary because everything's the same till you get to neon. In this case, because it's our noble gas right before it. So after we put neon in brackets, Then we get to our 3s2, that's both going to be full. And then our p, we're in the third, so we're going to have 3p, 1, 2, 3. And it should come up. There we go. 3s2, 3p, 3. So it's in that third box. It has 3 electrons. How many valence electrons? Well, this total valence electrons is the total amount of electrons in our highest principal energy level, which is 3. So that's 3, 4, 5. So we have 5 valence. All the other electrons are core electrons. Now for the D block, like I said, the principal energy level isn't quite the same. And it's really representing with that, that penetration that we showed. So when we looked at drawing the little diagram where I did the 1s, 2s, 2p, and you put it all in order, and you went through, this just represents that. So for the D block metals, the principal energy level is 1 less than the valence shell. So it's equal to whatever the period number is minus 1. So if we're looking at CS here, we have 4s2, but then when we get to D, it's 3d1. Then this is 3d2, 3d3, 3d4. And then if we get to GA, we're back to the P being at 4. So the D orbital is minus 1 of whatever our period is. So if we look at zinc, here's zinc. It's 30. Our period is 4, so we have 30 electrons. It's in group 2b. Our electron configuration is going to be argon, because argon is the noble gas directly before zinc. So argon is going to be in brackets. You're always using the noble gas before it. Not after it, before it. Because that's always going to be the same. That argon is going to be the same if we're talking about potassium, calcium, all of them until we get to zinc. Argon is going to be the same for all of that. The difference is going to be after argon. So then we run into 4s, and we go through 4s1 and 4s2. So our 4s orbital is full. But then we get to our 3d, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 4s2, 3d10 is going to be our electron configuration for zinc, because it's in that 10th one. This would look like this. It's completely full in that 3d. So that's how we would draw it. Now, if we're talking about valence, typically it only really has 2 valence electrons, because that's our principal energy level, which is that 4. If we look at arsenic, very similarly, but arsenic goes past the D. So that means all those 3 Ds are going to be full. So again, we have that 4s2. And then we go through all 10 Ds, so that's going to be 3d10. And then we get back into the P, and it's in the third little block. So that's going to be back to 4, 4p3. Bless you. So that's going to be our electron configuration for arsenic. Our argon in brackets, 4s2, 3d10, 4p3. And we have a total of 5 valence electrons. That's our 2 electrons in our 4s and our 3 electrons in our 4p. Now the F, there is some problems with some of the D block metals. But if we look at the D block metals, again, the principal is 1 less. Some of the transition metals have multiple electron configurations in which the ends only partially fill before the n-1 D fill, or it doesn't fill at all. So I'm going to show you which ones I mean. It's these. Notice that my 5s is only partially filled here. It's 5s1, 4d4. Same thing here, 5s1, 4d5. Ruthenium, this one as well. Here, palladium, we just go to 4d10. We don't have anything in the S. Silver, copper is another one. Chromium. So those are a little special. The question is, how do we know it fills that way? And The answer is experimentally we know it feels that way. That's not predictive. That's experimentally has been shown that what we see is that it does in fact feel that way. That's why we have transition metals, this irregular behavior. Now how can this happen? Well, remember your 4s and your 3d orbitals are pretty close to each other. So we can have where instead of our 4s being full, one of the electrons is in our 3d. Because they're really, really close in energy. They're not degenerate, but they're so close that if it makes the molecule feel more stable, it's likely going to do it. So that's why copper can bind different ways. It can bind with a 2+ or a 3+. We can have copper 3+ or copper 2+, and it has to do with the fact that we have this 4s and this 3d, and they're really close together, and we can have different electron configurations. You just have to know these. That's true of sometimes. So those that I have in green, that's the way that they will typically fill. Now on to the F block. The F block is our period number -2. So again, that's representing the penetration of that. And also the F block starts at 6. I know we put it under, but this top one goes right here, and the bottom one goes right here. So keep that in mind when you're trying to fill electrons there. And then the 4, so if we look at CE, we have our 6s2. Then we go to our 4f1. And then we have our 5d, which has that 1 electron in it. Because, again, it fits right here. So that F is 2-, and the D is still 1-. So we see that with, now we won't be doing too much reactions with those, but we should still be able to do the electron configuration. So if we look at EU, it's down here. EU has 63 total electrons. Now you don't have to fill out the full electron diagram for this one. It's going to be really long. So what we're going to do is look at the noble gas before it, which is xenon. We don't have to fill in anything before we get to xenon. We're just going to put xenon in brackets. Then, this is our 6s2. Our 4f, and it's in the 7th. And then, it doesn't really have any of the D. It actually fills here. So that's what we get with that one. And I'm going to talk a little bit more about the fact that it's 4f7 and not 4f6 and D1 in this slide. So just like with the D block, we have this problem with the F block as well. Not really a problem, but we see some inconsistencies because the orbitals are so close together, even though they are at technically different energies. So sometimes there's a D electron in the configuration, and sometimes there's not. So this one, CE, had that D electron, where this was 4F1, 5D1. But then if we look at PR, ND, PM, all the other ones, they don't have the D. The F just has one more electron. So instead of this being 1, 2, it's 1, 2, 3. Same thing with the EU that we just looked at. It doesn't have an electron in the D. Instead, it's 1, 2, 3, 4, 5, 6, and 7. So if it has a D, then you're counting the F's like we were doing 1, 2, 3, 4, 5, 6, 7, because that other one is in that 5D1. The ones that have the D's, you just kind of have to memorize which ones have the D's. That would be 58 has a D, 64, 71, 90 is interesting. 90 doesn't have any in the F because now all of its ones are full. 91, 92, 93, 96. And again, this is experimental, and 103. So those all have the d orbitals. It's really easy to do electron configurations until you get to that 6 or 7 energy level. When we get to these, you just have to know which ones have the d. And again, that's based on experimentation. So if we look at this one, the answer is C, but let's actually look at it. Here's V. First off, krypton is after V. So krypton is not going to be our noble gas in brackets. It's a noble gas that's before it, because it has all the same electron configuration up until that point. Krypton has more electrons and more energy levels filled. So krypton wouldn't be it. So A, B, and E all have to be wrong. So our noble gas before is argon. Then we have to go through our 4s, so it's 4s2, and then we're in the third, so 3d3. You do include that 4s2. D is incorrect because that 4s2 is not in argon's configuration, so you can't skip it. It has to be included. Now, like I said, everything in the same row of the periodic table, we can follow our trends. Everything in the same column has the same number of valence, so we have some predictive qualities. But there's still some differences of the atoms that can affect reactivity. So let's talk a bit about some trends in the periodic table. And these trends are based on the effect of the principal energy levels we have, the amount of electrons we have, the amount of shielding or de-shielding. So we'll break that down. So first we're going to start with atomic radius. So first, before we really talk about that, we have to know how atomic radius is generally described. Otherwise, we can't really talk about it. So there are several methods, and they might give slightly different numbers, but as long as you're using the same method, you can follow trends. So van der Waals radius is the non-bonding radius, and a covalent radius is a bonding radius. So clearly, that's going from nucleus to nucleus, what we're looking there, and we have 2 atoms, so it's divided by 2. Atomic radius is the average radius of an atom based on measuring large numbers of elements and compounds. So it's basically the average radius of the molecule. We're not going to be mapping out exact numbers, though. We're just going to be looking at trends. So it's okay that we're looking at the average radius. So let's look at the periodic table. First off, the radius increases going down a group. This makes sense because as we go down a group, the periodic table going down, we have more principal quantum energy levels, and we have more electrons. So if we have more principal quantum energy levels and we have more electrons, well, the atom's got to be bigger to have room for those electrons. So that trend makes sense. As we go down, hydrogen's real small, lithium's bigger, sodium's bigger, Rb is really big. This is all it's showing till, but of course we could follow those trends. Now, as we go across the periodic table from left to right, our size actually decreases. So you might be like, well, Dr. Cortez, as we're going across, let's talk about carbon to nitrogen to oxygen to fluorine. As we go across, fluorine has more electrons, so how can the size decrease? And that has to do with what we talked about, Coulomb's law, that the amount of charge affects our attraction. So as we go across, we have the same principal energy level. Carbon, nitrogen, oxygen, they all have a principal energy level of 2. So the size isn't getting bigger that way. But as we go across, carbon has only 6 protons in its nucleus. Nitrogen has 7, oxygen has 8. Oxygen has more of a positive charge in its nucleus, so it's going to pull more electrons towards it. So because we have a bigger positive charge, we have more electron pull for our electrons surrounding it. And again, our size of our atom isn't getting bigger because the quantum energy level is the same. So what we see is a slight decrease in atomic radius. The other thing to notice about this, here's just a general representation of the average number. And what I want you to notice is going across, let's again look at carbon, nitrogen, oxygen, where size is decreasing from 77 to 70 to 73 to 72, and our neon is 70. That's not a big decrease, but it is decreasing. But what I also want you to notice, if we take carbon and we go down, the increase is big. 77, 118, 122, 140. So the other thing to understand is that size difference going down is really big, whereas the size difference going across isn't negligible. It does make a difference, but it's not as big of a difference as when you're going down. So what that means is phosphorus is lower in the periodic table than carbon, but it's more to this side. That doesn't matter. It has an extra principal quantum energy level, so it's much bigger, because that's going to be a bigger effect. So going down is a bigger effect, but going across we do see an effect. It does get smaller, but it's not as big of an effect because, again, we have the same principal quantum energy level. And you can represent that here. This is just another representation where we're looking at these are all of them in group 1. And as we go down the periodic table, we see that size going down. So there's two ways you can look at it. That's just another graph. The next thing I want to talk about is shielding, because we talked about shielding a little bit. We're going to look at that in a little bit more detail. Shielding is not real important for hydrogen. We only have one electron. But once we get past hydrogen, it matters, because any electrons that are in a lower energy level can shield the nucleus. So that has a screening effect, and that means our outer electrons aren't as affected. Now, typically, electrons in the same principal energy level aren't screening too much. It's more the energy level's lower. So that's why the outer electrons don't experience the full force of the nucleus, and typically why our valence electrons are more available when we're talking about reactivity. So we talked about our nuclear charge. Let's really get into it. The effective nuclear charge, the actual nuclear charge that electrons might be receiving. So let's look at this. We're looking at lithium. We have 3 protons in the core. Our effective nuclear charge is a net positive charge that's attracting a particular electron, and we can look at that as Z minus S. So Z is our nuclear charge. That's going to be 3 for any electron we're talking about in lithium. We're talking about carbon, that's going to be +6. So it depends on what we're talking about. Then S is the charge due to the electrons in the lower energy level. So what we see is we have that 2 core electrons here. So this electron is only getting a net charge of 3 plus minus those 2 electrons, so 2 minus. So it's only getting a net charge of +1. So it's not getting the full nuclear charge. So that's all that's saying. Now, electrons in the same energy level are not contributing as much, so they're not really part of the calculation. They can affect the numbers slightly, but not enough for us to actually give us a headache of keeping them in there. So we're assuming that it's such a small amount, it's negligible, and we're not considering it in the equation. So our trends are typically that our S's have a lot of nuclear charge, but then when we get to P, D, and F, we're not getting as much, and that makes sense because those are higher energy levels. And that effective nuclear charge, again, is why, as we go across the periodic table, our atoms get smaller. So let's look at predicting which is going to be the larger atom. Now, again, this is a discussion of neutral atoms. Now, when we start discussing about charged particles, we're going to have to look at other things. But we're still going to be looking at effective nuclear charge, but it's going to change if we have an uneven pairing of electrons and protons. So right now, we're just going to focus on all of these atoms being neutral. So carbon versus oxygen. Here's carbon and oxygen. Which one's going to be larger? It's going to be carbon because it has less of a nuclear charge, so it's not pulling the electrons as close. Now, if we look at lithium and potassium, it's clearly potassium. It has more principal energy levels and way more electrons. That one's really easy. Now, if we look at carbon and aluminum, well, aluminum has a higher principal energy level, so aluminum is going to be larger. If we look at these two, though, typically iodine is going to be larger in general because it does have a higher principal energy level. But those are 2 opposing forces, so we might have to actually look at the numbers. So in this case, that one's a little ambiguous and we need a little bit more information, especially if we are comparing something like aluminum and fluorine. So aluminum does have a larger principal energy level, but fluorine is, well, that one's not a good example. Let's do chlorine and lithium. Those two are so far away and they're opposing forces, it would be really hard to tell. Because chlorine has a bigger principal energy level, but lithium has the least amount of nuclear charge. So typically, I'd predict iodine's probably bigger because it has the bigger bigger principal energy level. But because those are opposing, I might need more information because those trends are opposing. And there may be cases where that opposing trend is going to give us an issue. Now, for our transition metals, we are mostly just talking about our main group elements. But for our transition metals, they're also going to increase going down a column. That makes sense. But as we go across the d below, the size doesn't change that much. So for our main group, as we go across, the size changes. But for our d orbitals, the size doesn't change too much as we're going across. So they're all about the same size going across. Going down, still same trend. No difference with going down. So the reason why is the number of electrons in the outermost principal energy level are pretty constant. And we have a lot of, once we get to those d orbitals, we have a lot of inner core electrons. A lot of those are going to be pretty filled, so we're going to have a lot of blocking. So the net nuclear charge is going to be small and pretty much the same for all of them, and we're not going to get that smalling effect because we have more charge in the nucleus. Because we have too much blocking going on once we get to D. Elements, as far as our properties and electron configurations, elements in the same column have similar chemical and physical properties because of the valence electrons. So they have the same type of orbitals. Now they have more orbitals, and there are some things about them different. For example, size, which can affect reactivity. So size can affect that, so that is something to think about. So halogens, they're in 7A, and notice that even though they have a different principal energy level, 2s2, 2p5, our valence is the same. Now note, for bromine and iodine and whatever AT is, I don't even remember, doesn't really matter, we never use it. I am not including the D that would be between the 4s and 4p because they're not valence. So they're not shown here. The D's are not shown. But we know that it's 3d10, 4d10, 5d10. So keep that in mind with these. I'm not showing those. Also, with AT, we also have some F's in there. So those aren't being shown because they're not valence. So the valence, though, looks the same for all of these, and they have a very similar properties. They're not exactly the same reactivity, but they behave, they bond the same, they form the same type of anion, these form anions. So we see the same trends in bonding, though they might not be exactly the same. So let's talk about our electron configuration of our noble gases. So they all look the same. Again, when we're looking at argon, well not argon, krypton, xenon, all of those lower, I am leaving out the d orbitals. I am leaving out any F's for the lower ones because we're only looking at valence. Notice for these that all valence except for helium are full, meaning they have the, well, helium's also full, but they all have 8 valence electrons. Now for all of them, including helium, the possible bonding orbitals are completely full. And that's what makes them so stable, is that all of the possible orbitals that we predict by quantum mechanics are completely full. For everything other than helium, that's 8 electrons in the valence. Helium only needs 2 electrons to be full, because helium's in that principal quantum energy level of 1. So our N is equal to 1. So our L can only be equal to 0. So our ML can only be equal to 0. So all we can have is a 1s orbital. We don't have the possibility of p orbitals for helium because we don't have that second principal quantum energy level. So that's why it only takes 2 electrons to fill. Everything else has the highest principal energy level of 2s and 2p, and they're full. So that's our trend. And what we typically see is 8 valence electrons. And we know that they're non-reactive, and the reason why they're non-reactive is their orbitals are full. Their valence electrons are completely full. The noble gases are so unreactive that we call them really stable, and we'll often call them inert, meaning that they don't react. So this 8 valence electrons, we call this our octet rule. And quantum mechanical calculations show that an atom with 8 valence electrons, the full valence, are unreactive and they're very stable. Now again, that's not counting helium, which only has the ability to have 2 electrons in its full orbital. So for helium and hydrogen, 2 electrons is full. Conversely, elements that have 1 more or 1 less electron than 8 are very reactive. And we see that. Lithium doesn't have 8 electrons, and it's really reactive. And if we look at fluorine, fluorine only has 7 electrons in its valence. It wants to have 8, so it's super reactive. So what we see is group 1 and group 7 are pretty reactive. And then as we go group 2, it's not as reactive, though they still have a lot of reactivity, and so on. Halogen atoms have 7 valence electrons and are the most reactive nonmetals. Alkalized metals have 1 more electron than the noble gas before it. So it's actually our most reactive metals. And we see that they react pretty violently, they react pretty exothermically, because they really don't want that extra electron. So basically when we predicted the charges that our atoms were going to form, what we were predicting was the ability of our atom to have its electron configuration look like the noble gas that's closest to it. In other words, getting that valence electron diagram looking like the noble gas either directly before or directly after, depending on if we were talking about a metal or a non-metal. So everyone wants to be like the noble gas. Everyone wants that 8 electrons, with the exception of lithium and beryllium. They want helium's octet, so they only want 2. Hydrogen wants to look like helium, so it only wants 2. But everything else wants that 8 electron configuration. Helium's just special because it doesn't have any p orbitals. It only has that 1s, and that's full with 2 electrons. So in their reactions, alkali metals tend to lose 1 electron, because if they lose their 1 electron, remember, if we map out the valence of lithium, we could put helium in our brackets, and then we have that 2s1. If we lose the electron from 2s1, it looks like helium. If we look at sodium, we can put neon in brackets, and then it's 2s1. If we lose that 2s1, sodium looks like neon. Neon has 8 electrons in its orbital, so that's what the group 1 electrons, the group 1 metals are trying to do, and that's why they form a +1 charge. Because when they form a +1 charge, they're more stable, and they look like the noble gas before them. Sodium metal, very reactive, could be dangerous in large quantities, comes in the presence of water, catches on fire. Sodium ion, very unreactive. It's everywhere. You eat it all the time. Complete different reactivities. The reason why sodium ion is so stable is because it looks like helium, neon, the noble gas before it as far as electron configuration. Now the halogens, they need 1 more electron to look like the noble gas right after them. Chlorine gas, chlorine in its elemental form, very reactive, could kill you. Chlorine ion, you eat it all the time. Could kill you in too much, but overall, very unreactive. Chlorine ion takes 1 electron, and now it looks like argon. So the goal of forming those ions is to look like the noble gas and to have 8 electrons in its octet. So all of these accept an electron, so that it looks like the noble gas right next to it. So when we look at the periodic table and we learn the charges that represent it, magnesium, calcium, strontium, barium, they give up 2 electrons so they can look like helium. Then when we get to our metals here, aluminum wants to look like neon, so it gives up 3 electrons. When we're looking at our nonmetals that form ions, that form the negatively charged ions, they gain electrons until they look like the noble gas next to it. So if we look at nitrogen, nitrogen needs 3 more electrons to look like neon, so that's why it forms a 3 minus. It accepts 3 electrons, and then it has a full octet in its outer energy buffer. Oxygen needs 2 more electrons to form a full octet, that's why it makes a -2. Fluorine needs 1 more, that's why it makes a -1. And as you look at the nonmetals under oxygen, they behave the same way. They all need 2 more electrons to form the octet and look like the valence of the noble gas next to them. So that actually explains what we learned, I think, in chapter 2, and explains why this occurs, and why the periodic table helps us to predict that this occurs. So in the next 5 minutes, we're going to look a little bit about drawing the electron configuration when we have a charge. And we're also going to get to in the next class how this affects the sizes. So our electron configuration is going to represent either an extra electron or a loss of an electron when we draw it, if we have a charged particle. So anions are formed when we gain enough electrons to have that 8 valence electrons. So we're filling the S and P. If we look at sulfur, this is what sulfur looks like in its neutral form for its electron configuration. Sulfur needs to gain 2 electrons. So now its electron configuration looks exactly the same as argon. And if we add this up, we have 2 more electrons than sulfur should have. So pretty straightforward. That's how our electron configuration changes. And this is what its valence represents here. And it's completely full. Cations are formed when we lose all its valence electrons. So here's magnesium. Notice now the magnesium 2+ lost these 2 electrons. So we don't put 3s0, we just get rid of it. And now it actually looks exactly the same as neon, if you were to map out neon's electron configuration. If we look at aluminum, again, aluminum loses 3+, it loses our 3p1 and our 3s2 to form that 3+. So notice they're gone, and this is our configuration. If you look at Fe, we're losing our 4s2, and that's going to form our Fe2+. So we're losing the valence, we're not losing the inner electrons. We can also form 3+, that loses one of them from the D. And here's copper. And again, we're losing that 4s1 for copper +1. And I just want to answer that iClicker question. And then for this one, 4d, if you look at Sn neutral and you lose all its valence, it's krypton 4d10. That's the loss of all the valence. Have a good day.